So we looked at direct comparison tests for trying to determine convergence or divergence, and we saw that that relied on the two functions having a sort of bounding. One of them is trapped between the x-axis and the other function. But if the inequality is just on the wrong side, that technique's not going to work. So we want an approach that doesn't look at their size, but the rate at which they're heading down to the x-axis. Remember, I mentioned before that it's not enough just to go down to the x-axis. You need to go down there fast enough. And so this approach looks at the rate at which we're approaching. Are two functions heading down there at the same rate? And that's what we call the limit comparison test. We've got it up here. Again, this is actually based on direct comparison. When we prove it here in a second, you'll see that. So they do need to be positive and continuous, just like for direct. But now we don't care who's bigger or who's smaller. What we're going to be interested in is that limit. So we're going to take the limit there as x goes to infinity of their ratio. And if you get some L that's between 0 and infinity, what you've established is that they have the same growth rate, right? That out at infinity, one is basically just a multiple of the other. F is just L times G. So we're hoping to establish two functions that have the same growth rate. And if we know that the integral of one converges, then the other one does, or vice versa. If we know the integral of one diverges, then we know the other one does. And that's our conclusion statement there. If that limit comes out to be a number between 0 and infinity, then we know both those integrals converge or they both diverge. The trick is just to find something that we do know how to integrate that would compare nicely. So we looked at a certain class earlier, integrals of stuff 1 over x to the p. And that's what we'll usually use for comparison purposes. But we'll look at an example in a little bit. But let's see why this is true then. So say we have this situation. What does this mean that that limit eventually is L? So, well, let's think about this. Let's look at both cases. Let's say, and just for the purposes of proving it, we just got to pick one of those guys. Let's say that the integral from a to infinity of g of x converges, and that limit comes out to be L, like we said. The idea here is I want to try and rely on direct comparison, since we already have that and we've already proven it. So what I'd like to do is somehow argue that I can get something bigger than f that also converges. So if this is eventually approaching L, it's getting closer and closer and closer to L. That means eventually that ratio has to be less than L plus a little bit, right? So I'm just saying some number bigger than L. Because if you're getting infinitesimally close to L, you got to eventually be less than a number bigger than L. I guess we could have just said plus 1, but epsilon, some amount bigger than L, which means that f of x can be bounded above by g times that number. But we also know from the statement that these guys are positive. So, and now what do we have? We have f is bigger than 0 but less than this, but we know that the integral of g converges. And this is just some constant. So since the integral from a to infinity of g of x converges, then multiplying that by a constant, L plus epsilon, that converges. So the integral of the smaller function f of x must also converge by what we established previously in dct. So what we're doing is, the problem is that in dct, these guys could be, the problem is if those guys are crisscrossing, we don't get the bounding that we want. But that's OK, because if this is getting closer and closer to L, I can put some upper bound on it, L plus epsilon, which allows me to get f trapped not underneath g, but g times some amount. And then we can use the direct comparison. On the flip side, if we wanted to prove the reverse, that if g was divergent, then all we'd have to do is say, well, if this is getting closer and closer to L, it's eventually bigger than L minus epsilon, and then we have a direct comparison argument there as well. So the limit comparison theorem there is based entirely off of DCT. We're using DCT to prove that. But it's for situations where DCT wouldn't work because the inequality is the wrong way. But here we can use it when we know the two functions have the same growth rate. And we'll look at an example of this.